Good morning. Today I want to take you behind the walls of Mount Sinai and explain how our HVAC infrastructure supports patient care, research, reliability, and energy efficiency. We will follow the system from the room back to the air handler, through the hydronic loops, and into the central plant. The goal is not to turn everyone into a mechanical engineer. It is to give you a practical understanding of what the major systems do, how they connect, and what to look for during the tour. Most people think of HVAC as heating and cooling. In a hospital, it is clinical infrastructure. The same systems that provide comfort also control ventilation, filtration, temperature, humidity, and pressure relationships. Those conditions help protect patients and staff, support operating rooms and isolation rooms, enable laboratories and sterile processing, and remove heat from equipment and data spaces. The operating requirement is therefore larger than comfort. A room can feel acceptable and still be outside its required airflow or pressure relationship. Our responsibility is to maintain the conditions that the approved design and clinical program require. Before we discuss equipment, we need to understand the scale of the energy involved. Annual utility spending. Electricity is the largest portion because chillers, compressors, fans, pumps, and cooling towers are major loads. Energy management therefore includes both operating savings and outside funding. Utility incentives may offset part of the cost of qualifying chiller upgrades and other verified efficiency projects. We still need sound engineering, commissioning, and measurement and verification. Demand response is different. During summer grid events, we switch load from utility power to generator power, reduce approved non-critical electrical load by utilizing setbacks while protecting patient care. On the steam side, interruptible natural gas service requires dual fuel readiness. When the utility calls an interruption, the boilers transfer off natural gas and onto fuel oil before the interruption begins, then stay on alternate fuel until it ends. The utility spend makes more sense when we look at the campus scale. The Mount Sinai Hospital campus, shown here, is about 5.3 million square feet across 15 buildings. It includes more than 40 closed hydronic systems, hundreds of air handling units, thousands of VAV terminals, and thousands of BAS control points. The complexity is not just the number of components, it is the number of dependencies. A single sequence, valve, sensor, or pump can affect many rooms. The reverse is also true. A verified improvement can be repeated across a large portfolio. Scale multiplies both operational risk and energy opportunity. To understand those dependencies, follow a room condition backward. The room depends on a zone terminal, often a VAV box, to control airflow and reheat. The terminal depends on stable air from the air handler. The air handler depends on chilled water, heating water, steam, electrical power, drainage, and controls. Those hydronic systems depend on pumps, heat exchangers, valves, and the central plant. The plant depends on electricity, fuel, water, and utility continuity. BAS controls and plant operations people span every layer. That is why a room complaint may be only the symptom. The root cause could be a local sensor, a VAV damper, an air handler coil, a pump sequence, or plant capacity. Project decisions also travel through this same chain, so changes must be evaluated as part of the complete system. The boiler plant adds heat to water and distributes that energy as steam. Start with make-up water treatment. The softeners remove hardness that could form scale on boiler heat transfer surfaces. The dealkalizer reduces feed water alkalinity. Treated make-up water then combines with returned condensate in the receiver. From there, the deaerator heats the feed water and removes dissolved gases, especially oxygen, that contribute to corrosion. Feed water pumps move the water toward the boilers, and the economizer recovers heat from the flue gas to preheat that water before it enters the boiler. 6 boilers provide 360,000 pounds per hour of installed capacity and feed the campus steam header at roughly 125 psi Greg. Steam supports heating, humidification, sterile. After steam gives up its heat, recovering the condensate returns hot, treated water to the cycle and reduces make-up water, chemical use, and fuel demand. The chiller plant does the opposite of the boiler plant. It removes heat from the buildings. The easiest way to understand it is as 3 separate circuits. First is the chilled water loop. Water leaves the plant at about 42 degrees, absorbs heat at building coils, and returns at about 56 degrees under representative design conditions. Second is the closed refrigerant circuit inside the chiller. Refrigerant absorbs heat in the evaporator. The compressor raises its pressure and temperature. The condenser transfers that heat into condenser water, and the expansion device drops the refrigerant pressure so the cycle can repeat. Third is the condenser water loop. Water returns from the cooling tower to the chiller at roughly 85 degrees, absorbs the rejected heat in the condenser, and travels back to the tower at roughly 95 degrees. At the tower, airflow and evaporation reject that heat to the atmosphere. Those temperatures are typical reference values, not fixed set points. The key point is that the tower is part of the condenser water circuit, not the refrigerant loop. Plant capacity reaches the buildings through hydronic loops. Most of the chilled water, heating water, dual temperature, and specialty laboratory systems are closed loops. Heat exchangers transfer energy between the plant and building sides while keeping the fluids separate. Pumps, often controlled by VFDs, move the water. Control valves regulate coil capacity, and return temperature and flow tell us how much useful energy was delivered. Condenser water is different. It is a separate recirculating system that is open to the atmosphere at the cooling tower. Because evaporation concentrates dissolved solids and the tower is exposed to air, that loop requires dedicated water treatment, blowdown control, monitoring, and maintenance. In every loop, poor delta T, a restricted strainer, a drifting sensor, or an incorrect valve position can increase energy use without improving room conditions. The air handler is where plant capacity becomes conditioned air. A typical mixed air unit combines controlled outdoor air with return air, then moves the air through filters. A preheat coil tempers very cold air and helps protect downstream components. The cooling coil lowers the dry bulb temperature and, when its surface is below the air's dew point, condenses moisture for dehumidification. A humidifier adds moisture where the space requires it, and the supply fan moves conditioned air through the duct system. The fan VFD adjusts output to system demand, while dampers and coil valves regulate air mixture and heating or cooling capacity. Not every air handler contains every section. Critical care, isolation, and laboratory systems may use different outside air, filtration, exhaust, redundancy, and control arrangements. The actual approved sequence governs how each unit must operate. At the zone level, the VAV box fine-tunes airflow and temperature. A sensor reads the room temperature, the damper modulates, the box maintains its allowed minimum airflow, and reheat operates when the space needs heat. In an ordinary comfort zone, airflow can often reduce as the cooling load falls. In a critical space, ventilation and pressure requirements may set a higher minimum. The direction of airflow matters. Operating rooms are typically maintained positive to adjacent areas, so air flows out. Airborne infection isolation rooms are negative, so air flows into the room and contaminants are contained. Protective environment rooms are positive to help protect highly susceptible patients. Laboratory relationships depend on the specific hazard assessment and program. There is no single temperature, humidity, air change, or pressure value for every hospital space. The adopted code, ASHRAE Standard 170 edition, approved design, and clinical use determine the requirement. The BAS coordinates the system, but it cannot compensate for failed field equipment. The control loop starts by sensing temperature, humidity, pressure, airflow, and equipment status. The software then applies set points, schedules, resets, trends, calibration, and field checks confirm whether the commanded action actually occurred and produced the intended result. A sophisticated sequence cannot overcome a drifting sensor, a stuck damper, or a failed actuator. BAS data is most valuable when operators use it to identify patterns, compare performance over time, and verify the physical system in the field. Efficiency must always preserve clinical requirements. We start by eliminating unnecessary runtime. Approved setbacks can widen temperature bands or reduce airflow and equipment schedules in offices and other non-critical areas when they are unoccupied. Those setbacks are never applied blindly to operating rooms, isolation rooms, lab. We then reset set points based on actual demand, chilled water temperature, condenser water targets, supply air temperature, duct static pressure, and hydronic differential pressure. Every reset must protect coil dehumidification, minimum airflow, room pressure, and equipment limits. VFDs let pumps and fans match output to demand, while plant sequencing prevents extra chillers, boilers, pumps, or tower cells from running unnecessarily. Demand response reduces peak kilowatts during a grid event. Energy efficiency projects reduce kilowatt hours every day. Utility incentives can offset qualifying project costs, but savings must be commissioned and measured. BAS retuning, heat and condensate recovery, reliable steam traps, and field verification complete the strategy. During a natural gas interruption, the boiler plant transfers to fuel oil before the interruption begins. The guardrail remains absolute. Never trade required clinical conditions, redundancy, or continuity for savings. Reliability is not created by equipment alone. It comes from a disciplined operating model. The team monitors BAS trends, completes rounds, and manages water chemistry. It performs preventive maintenance, predictive testing, and calibration. It responds to alarms and emergencies 24 hours a day, 7 days a week, 365 days a year. Changes are controlled through methods of procedure, lockout-tagout, shutdown planning, and coordination with affected departments. After work is completed, we verify operation through commissioning, compliance checks, and ongoing trending. The 214-person engineering operations team, 37 managers, and 177 staff supports one interconnected campus system. Safe, reliable, and efficient performance depends on ownership at every step. The takeaway is simple. This is one connected system, and it produces 3 outcomes. First, protect care by maintaining the environmental conditions required by each clinical and research space. Second, sustain continuity through reliable equipment, redundancy, 24/7 coverage, safe changes, and disciplined maintenance. Third, manage cost and emissions through efficient operation, demand response, utility incentives, approved setbacks and resets, dual fuel readiness, and verified savings. The investment priority is reliable infrastructure, trustworthy sensors and controls, disciplined operations, and measurement. Every energy measure must protect the clinical requirement, preserve reliability, and produce measurable results. We should capture available incentives, but the incentives should support a sound engineering project, not create one. Engineering is core clinical infrastructure. When HVAC performs well, the hospital performs well. This floor plan will help orient us before we enter the central plant. During the tour, follow the energy path we just reviewed. Identify the boiler and steam systems, the chilled water and condenser water sides of the chillers, the pumps and distribution piping, the controls, and the electrical and safety interfaces. The goal is to connect each large piece of equipment back to the rooms and services it supports.